Hi everyone, this is going to be the first of a 5-part series of videos I'm making on naming. This first one is just going to focus on type 1 ionic compounds, and it's not going to include any polyatomic ions. So technically these are going to be binary compounds, binary meaning just two elements. Element A, element B, and type 1 meaning we know the charge of that cation. So let's go into this in a little more detail. So first of all, I just kind of answered this. What are type 1 ionic compounds? Or in other words, what makes a compound type 1 versus another type? Well, type 1 is when the cation, which is the positive ion, which is usually always going to be the front one, when it has a fixed charge, a constant charge that we always know what it is. It's not a transition metal where it can have variable charges. So anytime the metal has a fixed charge, it's going to be considered type 1. Here's some background questions we need to know. First of all, we have to understand metals versus nonmetals, where they are on your periodic table. So on the periodic table, the bold line kind of marks where the metalloids are. The metals are to the left of it. So the metals are going to be all of these elements except for one, and that's hydrogen up there by itself. So again, all of these are metals. The nonmetals are going to be those in the right corner to the right of the bold line, and the metalloids kind of fall on the line. Now, why do we need to know metals versus nonmetals for naming ionic compounds? Because ionic compounds are always one metal plus another nonmetal, with some exceptions which we'll get to in the other videos. So when you see a metal and a nonmetal, you know that it's ionic, which gets a certain type of naming. If it's nonmetal bonded to nonmetal, that's going to be covalent. You name it differently, which you'll see in one of the later videos. So you have to be able to identify when it's a metal and a nonmetal. Next thing you have to know is which ions do elements form. So on the periodic table, yours may be marked, but keep in mind during tests and quizzes, at least at the Chem 1-2 level, you're going to be given a fresh copy of this, so whatever annotations you make on it when you study won't be there for tests and quizzes. So you can mark it up all you want, but you got to know this stuff. You got to memorize certain things. And this first group, which is 1 or 1A, it always forms a 1 plus cation, or just a plus. The second group forms 2 plus. This third one forms 3 plus, although really it's just aluminum there. The one with carbon tends to not form ionically. It does happen, but it's very rare. So we generally will ignore that one. And then N, O, and F, these are 3 minus, 2 minus, and minus. And that's because we have 5 valence electrons here, 6 valence electrons, 7 valence electrons. These are going to want to gain electrons. So for example, N, P, those have 5. They're going to gain 3 electrons, giving them a ionic charge of -3, or 3 minus. You do the number first. This group here with the O is 2 minus, and this group is minus. Don't forget, noble gases are not going to bond, so these aren't involved. So again, we have plus, 2 plus, 3 plus, generally skip, 3 minus, 2 minus, minus. Transition metals. So you just have to understand what these are. These are not type 1, but it's important to realize that. So transition metals are the metals in the middle of the periodic table that can have variable charges. So we can't just name them the same way. And it's usually shown as just this box here, but it actually extends down as well. So elements like tin, bismuth, lead, these are going to be transition metals too. So it's more like a rectangle with a little triangle hanging off of it down there. So these are your transition metals. Anytime the metal in a compound is one of those, it's not going to be a type 1 metal. You can't name it with the type 1 rules. You have to use type 2 rules, which you'll see in the next video, and that means your Roman numerals. And the last thing you have to know is a 3-2-1 rule. That's the name we have for 3 elements that are within the transition metals, but always have a fixed charge, so they're considered type 1. And that's aluminum, zinc, and silver. Al always forms 3 plus, Zn always forms 2 plus, Ag always forms plus. So even though these two, zinc and silver, are located within the transition metals, they're considered type 1 because they have a fixed charge. So you could see those up here with type 1, and when you name those, you're not going to say silver 1, and then whatever the nonmetal is, and you're not going to say zinc 2, and if you have no idea what I'm going like with this, you'll see in the second video. You don't name them with the type 2 rules, you name them with the type 1. So that's the background you have to know. Just a refresher, I kind of summed it up. Which cations are considered type 1? Again, it's the ones that we always know the charge of, there's no question, which means the group 1 metals, which are always plus, the group 2 metals, which are always 2 plus, the 3,2,1 metals, which are aluminum, zinc, and silver. So right off the bat, we can literally read off the list here. It's going to be lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, barium, radium, aluminum, zinc, and silver. Those are the only metals that are going to be type 1. Now, there is one other here I'm going to mention. It's ammonium. This is a polyatomic ion, which I told you I'm not going to include in this video. But because ammonium, which you probably have a sheet that looks like this, ammonium has a charge of NH4+, it's a cation. And since it's always NH4+, when ammonium shows up as a cation in a compound, it's considered type 1 because there's no question about it. So these are the cations to look for. Now, in terms of which nonmetals make up the second half of a type 1, it doesn't actually matter. There is no, because with all the nonmetals, there's never any variety, there's never any variation. N is always 3 minus, S is always 2 minus, Br is always minus, O is always 2 minus. There's never any variability among the nonmetals, so we don't even consider it here. So all you need to look at to determine if something is type 1 or type 2 is the first part. If the first part of it is one of these metals or ammonium, it's type 1. If the first part is one of these transition metals, it's type 2. Oh, and if the first part's a nonmetal, then you have nonmetal bonded to nonmetal, that's covalent. All right, let's do a couple quick examples here. So for example, what compounds form when calcium and chlorine bond? So calcium on the periodic table is in group 2A, and you should know that it forms a compound, it forms an ion of Ca2+. You really should get in the habit of putting the 2 before the plus. Charges should be written that way. So it's Ca2+, and chlorine is Cl-. Okay? Now, when we write a compound, the whole point of a compound is to cancel out the charges. So how do I cancel out a 2+ and a minus? Well, you're going to need 2 of these, because that really means 1 minus. You're going to need 2 of these chlorines to cancel out the 1 calcium. So your formula is going to end up being 1 calcium and 2 chlorines. Now the way we can do this 90% of the time is using this crisscross method, where you take the number here and put it after this element, and the number here, now what's the number? It's not shown, but it's a 1. There's really a 1 there. You take that number and you put it here, but again, we don't actually write a 1 when it's a 1. So the 2 goes after the Cl, the 1 goes after the Ca, and our result is CaCl2. And that's the correct compound for this. Now when it comes to naming it, naming type 1 ionic is very simple. You simply state the name of the first one, and you state the name of the second one, changing the N to "ide." You don't change it depending on how many there are. You're never going to say di for this. You're not going to say calcium dichloride. That di or tri or mono, those are only for covalent naming, which you'll see in one of the later videos. So literally, you look at these and you just say calcium chloride. You're not indicating how many there are. It's up to, if you see it written calcium chloride, it's up to you to know or to figure out how many there are based on the periodic table. So it's not like you're going to say it's calcium dichloride, CaCl2. You would just say calcium chloride. Simple. Another example, aluminum and oxygen. So aluminum on the periodic table is in group 3A. It's part of that 3-2-1 rule, has a charge of 3+. Oxygen, O2-. Okay? I would just use the crisscross rule for this. You just zip them across like that. The 3 goes with the O, the 2 goes with the Al, and you end up with Al2O3. And if you want to see how this works kind of more logically instead of just like a quick little game like that, think about it. Imagine you have a certain amount of aluminums with a charge of 3+ and a certain amount of oxygens with a charge of 2-. Well, if you want to balance these out, you need to figure out how to get them both to be the same number in opposite charges. So like right now, we don't have enough negatives. So if I had another oxygen, well, now the problem is I have 3+ and 4-. That's not going to work. Let me add another aluminum. Okay, so that didn't help. But now I have 6 positives and 4 negatives. Notice if I had a third oxygen, I have 2, 4, 6 negative and 3, 6 positive. I now have 6 and 6. It balances, hence Al2O3. Last example, zinc and sulfur. So zinc is part of our 3-2-1 rule. It's a type 1 metal. Zinc is Zn with a charge of 2 plus. Sulfur is S with a charge of 2 minus. Remember I said the crisscross method works 90% of the time? This is one of those times where it doesn't totally get you the right answer. You can still use it, but then you have to go one step beyond. If you looked at this without me saying the crisscross rule, it's probably even easier. How many of each of these do you need to balance it out? Well, 1, right? It's 2 plus and 2 minus. So the formula is simply going to be ZNS. Now, if you do the crisscross rule, you would end up with a 2 here and a 2 here, but you would have to simplify it down. For any ionic compound, and this is important, for any ionic compound, you have to simplify it down to the simplest numbers. So you cannot report Zn2S2. That's false. That is wrong. You would have to simplify this down to Zn, let's put a subscript S, ZnS, okay? Zinc sulfide, like that. Oh, and I forgot to name the one from before, but 1 sec on that. So yes, ionic compounds have to be simplified down to their simplest form always. Covalent, on the other hand, which you'll see in one of the later videos, you do not simplify down. So if you have, and I'm getting ahead of myself here, but if you have like dinitrogen tetroxide, and if you see what I mean, it's going to end up being dinitrogen means 2 nitrogens, tetroxide means 4 oxygens. You leave it just like that. You don't simplify that down to NO2. So when it's covalent, you leave it. When it's ionic, you have to simplify it. I said the name of this. Again, it's super simple to name these. You just state the first one, state the second one, change the end to "ide." So this becomes zinc sulfide. And you might say, well, isn't it like sulfuride, or what? How do I exactly know it? It's just going to be zinc sulfide. This previous one, aluminum and oxygen, forms aluminum oxide. Simple as that. You don't say dialuminum trioxide. Leave that for covalent. It's just going to be aluminum oxide. And just to quickly comment on what the names of these nonmetals are going to be when you turn them into ions. So starting with the halogens, which is group 17 or 7A, it's very simple. Fluorine becomes fluoride, then chloride, bromide, iodide. Starting with oxygen, now notice I skipped AT, that's astatine. I mean, theoretically it could bond, but this is such a rare element, we almost never include it. But if it did, it would be astatide. Starting in the next group, with oxygen becomes oxide, then sulfide, then selenide. Selenium becomes selenide. The one below it, tellurium, very uncommon. We generally don't use that as an example, and it kind of borders the line between metal, non-metal, metalloid. It's just not a good example we use. The next group, we have nitrogen and phosphorus are kind of the two ones that will commonly form these bonds. Arsenic tends to be more like a metalloid type that's not really going to be involved in these. But anyway, you might think this would be nitrogide and phosphoride. That's a very reasonable thing to think, but it's not. You just got to memorize. N becomes nitride and P becomes phosphide. And then actually carbon can form as an anion. It's very rare, but when it does, it forms carbide. You may have heard of that term before, like a tungsten carbide or something. So anyway, those are the common anions, the negative ions, what they would be after they bond. Okay, so just for the last part of the video, I have a few sort of rapid-fire examples. This says, name the following type 1 ionic compounds. Notice all the 2s, all the 3s, all the 1s that aren't written, but they're there. When it comes to naming, doesn't matter. You can just rapid-fire your way through this as long as you're familiar enough with the symbols. Aluminum fluoride, zinc oxide, sodium phosphide, calcium phosphide. See what I mean? It doesn't actually matter how many there are. As long as they're type 1, you can just name them like this. And how do I know they're type 1? Because I know that aluminum has a known charge, 3+. Zinc has a known charge, 2+. Sodium is plus. Calcium is 2+. Plus, plus, plus. And look, the more you do these, the more you'll memorize the charges of certain elements like this. But because these are type 1, you don't need to clarify the name in any way. You just state the first one, state the second one, change to I. So again, aluminum fluoride, zinc oxide, sodium phosphide, calcium phosphide, lithium chloride, rubidium selenide, silver nitride, potassium bromide, aluminum sulfide. If you want, maybe you could pause the video and reverse and try to quiz yourself on these again. But they're very simple when you do them this way. Takes a little bit more effort to go the opposite way, which is to write the compounds out. For example, for this, I can't just say LiO, ZnP, KiRbS. You can't just blindly do it that way, because remember, these have different charges, so they're not going to form one-to-one ratios always. So what I always say to do first, don't try to do it all in your head and write the final answer down. Okay? Usually when you do that, you get it right like 80% of the time, but you can do much better than 80% of these. So what I always say to do is write the ions down with their charges, then write the final formula. So lithium oxide is lithium bonded to oxygen. Use your periodic table. Lithium is Li plus, oxygen is O2 minus. Crisscross rule, the 2 goes with the lithium, the plus goes with the 1 goes with the oxygen. Our formula is Li2O. Zinc phosphide, zinc is 2 plus. Phosphide is P3 minus. By the way, if you have your polyatomic ions sheet, be careful. On this sheet, we have phosphate and phosphite, not to be confused with phosphide. Phosphide is just regular old P, phosphorus. Similarly, we have sulfate and sulfite, not to be confused with sulfide. Sulfide is just S. So anyway, when we form these, you crisscross a 2 and the 3, and your product is going to be Zn3P2. Potassium iodide is K plus and I minus. Notice the one-to-one ratio, crisscross the 1s, Ki, if you want to do the lines. Rubidium sulfide. Rubidium is Rb with a plus sign. Sulfide is S2 minus. And when I say with a plus sign, I really mean with a charge of plus 1. You crisscross them, we're going to need Rb2s. If you want to quiz yourself more, maybe pause here and try to work the rest of them out and then hit play. Silver chloride. Silver is one of the 3-2-1 rules, and it's the 1. So it's Ag plus and Cl minus. Notice the 1-to-1. Crisscross them, AgCl. Oh, and I've kind of been forgetting to, I said forgetting to name them. They're actually written here. So I don't need to name them, but clearly it's lithium oxide, zinc phosphide, potassium iodide. Again, very simple to name. The last one here, calcium bromide. Calcium is Ca2 plus, bromide is Br minus. You crisscross them, you get Ca1Br2, don't write the 1, CaBr2. Cesium oxide, Cs with a charge of plus, oxide with a charge of 2 minus. You crisscross them, you get CS2O. Aluminum selenide. Aluminum is Al3 plus. Selenide is selenium, which is Se2 minus. We have a 3 plus and a 2 minus. You crisscross them, you end up with Al2Se3. And finally, magnesium is Mg2 plus. Sulfide is sulfur, which is S2 minus, not to be confused with sulfate and sulfite, which are both polyatomics. Notice the 2 to 2, it's going to cancel out, and it's just going to be Mgs. Now, if you crisscross it and put Mg2S2, you have to simplify that down, otherwise it's wrong. So the answer is Mgs. So that's it for type 1 with no polyatomic ions. The next video is going to be type 2, which are the transition metals.